another mortalized class. So I recorded a class yesterday and accidentally hit the button where it's recording in the other direction. And then when I was watching later, I noticed everything was backwards. All the writing on the board was backwards.
You can switch that.
Yeah, well, this works. All right, so the class left off. Sort of a recap of some of the stuff we did yesterday. I have a 24/9 nanocoulomb charge here, and the reason I'm going for the fraction is just so that the math works out and works out nicely. And I wanted, what is the potential? Ignore that. What is the potential, otherwise known as electric potential, 1 meter away, 2 meters away, 3 meters away, 4 meters away from that charge? So just starting out, first electric potential is V. And what is the formula if you have a point charge?
KQ over R.
All right, so therefore, what is the electric potential at 1 meter away?
9 times 10 to the 9 times 10 to the 9.
Without a calculator. You can do it without a calculator. I believe in you.
Oh, 24 times 10 to the 9. Yes? No?
So close. That's nanocoulombs.
Fudge. 24 times 10 to the 3rd.
Nano is 10 to the negative 9th.
Oh, fudge. 24.
Yeah, 24. 24 what?
Newton coulomb. No. I'm just spewing words.
You are.
You love it. Volts.
It's a dream come true. All right.
Volts.
Oh, okay, 24 volts. 2 meters away?
12.
8 volts.
All right. We were on a roll there. All right. Down here, if it's negative,
Negative 12. 24 volts. I'm so sorry.
somebody say 18. I'm just hearing, you're spewing words and I'm just hearing spewed words. All right, here.
Negative 12 volts.
Although this one right here, it sounded like we almost got a little unison going. That was nice.
Negative 8 volts. Negative 6 volts.
All right. What's the direction, in the top example, what is the direction of the electric field?
Away from 0 meters.
Okay.
Outward from it.
And potentially we have some other color here. So my electric field is going that way. So much nicer. They thought they could hide these from me. All right, so that's the direction of the electric field. What about in the bottom case? So in terms of this region right here, which way is it going? Yeah, be going that way. So towards that negative charge. In both cases, what generalization can we make about the relationship between the electric field and the electric potential?
They wouldn't be opposites.
What do you mean by that?
State your question one more time.
What is, from this, what generalization can we make about the relationship between the electric field and the electric potential? I feel like the spirit of what you said was right, but the wording is off.
So,
In terms of opposite, like the electric field is going away from the point charge. So like, if you were to draw,
So going towards the point charge in this case, though.
I don't know.
All right, someone else?
Electric field is thrown towards where it's more negative. this?
Smaller?
Sure.
You said more negative, there are no negatives here, so that's,
Yeah, it's a less positive number, yes.
or a smaller number? Is that what you,
Yes.
more negative or less positive?
Yeah.
I think smaller is generally the word for it. Okay, yes, that's it.
We're all just spewing words there.
It is, it's just,
It's physics and American.
I think Shakespeare would be proud. All right, so the electric field points toward, or towards, depends on where you are, the lower potential. And again, when I say potential, that's understood electric potential and not energy. Janice,
Is that like a general rule, or
Yeah.
is that?
that's a general rule. And with a lot of these cases, with a lot of these things, if you can sort of visualize a simple example and then, well, actually, we simplify, we look at a simplified example and then generalize from there. We do that quite a bit in this course. So, yeah. More than just this case. There's one other relationship that I have not been as explicit about as probably should be. So I have a 1 nanocoulomb charge here. Talk about the potential if I'm here. Let's say this is some distance r away. The electric potential here versus, let's go on the other side. If I'm the same distance away, what's the electric potential here versus the electric potential here because of the 1 nanocoulomb charge?
They're the same, if they're the same distance away from the charge.
Even though they're in opposite directions?
Yeah.
Radial vector, going away from more charge.
Is the electric field here the same as the electric field here there?
Would you have to distinguish whether or not the charges away from the plus one and positive or negative?
Say it again.
Would you have to establish if those points are positive or negative?
These points?
Yeah.
No, electric potential doesn't require anything at that other point. It's just some location in space. Is the electric field here the same as the electric field here? All right, so we have an unsure yes,
Yeah,
a more confident yes.
no,
Why not?
because it's going away from the positive point charge, so it'll be going in opposite directions.
Yes, electric field is a vector. So that vector and that vector are not the same. The magnitudes are the same, but the actual vector itself is not the same because they're in opposite directions, as Tina said. But you're claiming that the electric potential is the same. Why is the electric potential the same, but the electric field is not?
Is the potential, is that a scalar measurement?
Yes, it is. All right. So, matter of fact, any place a distance r away from this, that's supposed to be a circle of radius r. Those all have the same electric potential. Matter of fact, we could do a sphere if I had my three-dimensional drawing board here. This right here is known as an equipotential surface, which I made reference to last week sometime. In theory, a charge could move along an equipotential surface, and it does absolutely for no work. It doesn't take any energy for a particle to travel on an equipotential surface.
You said that the electric field was different, but the electric potential was the same.
Yes. And I'm gonna redraw this. Don't panic. I'm erasing it. I'm gonna redraw it because I actually want a better circle than that. All right. So this was a positive 1 nanocoulomb charge. I talked about the electric field. Oh, before we do that, so that's an equipotential surface. There'd be another one there-ish. There's this whole bunch of rings here of equipotential surfaces. Talk about the electric field from this positive charge. Well, you know about the, okay, got some hand gestures there. Looks like I grabbed the wrong one. So, what's the relationship between these electric field lines and the equipotential lines? It's true in this case, and it's generally true. The relationship between the electric field lines and the equipotential surfaces.
They're moving like in the same direction. May not move that much.
You sort of picturing these ripples of water moving outwards?
I mean, like, the electric field lines are going outward and so are the circles.
I hear what you're saying, that's not sort of what I'm going for there. Because you could also look at the circles as going inwards, depends on if you're focusing in or expanding your vision. So, sort of a potentially a hint here. We're looking for a geometric relationship. In unison would be really great right now.
Follows.
You're spewing hand gestures now.
So, I guess the
Mic's on.
electric field, like, the outer part of it forms a circle,
The outer part of the electric field forms
like,
a circle.
like the arrows.
Apparently it's devolved into a read my mind exercise. Yeah, oh, well, actually, you see it one other place. If I have the parallel plate capacitor, I got the positive and negative charges, my electric field is traveling this way. We assume the even distribution of charge across the plates, and matter of fact, the plates should, if the charges are distributed, the plates should be equipotential surfaces. And if we drew the equipotential lines, they would actually look like this. These are equipotential lines. Perhaps a little bit more obvious to see here, the relationship between the equipotential lines and the electric field.
Perpendicular.
Perpendicular.
More than specific, more than that.
They're perpendicular.
And so we have a second generalization, is not only does electric field point towards the lower potential, the electric field is perpendicular to equipotential lines. Go ahead, so the equipotential surfaces. If it's not that way, then that means that it's not in any sort of equilibrium and that charges are going to start moving around until this is the case. All right, so those are two concepts that I sort of glanced over or ignored before. But when the next week's lab, what you're going to do is you're going to have sort of like parallel plates. It won't exactly be parallel plates, but you'll have two parallel conductors. And you'll find equipotential lines because that you can measure. You take a voltmeter or a multimeter on voltage and you find the places where the potential is the same. And then from that, you can figure out where the electric field lines are. All right, now I want to jump back over to capacitors, which is, I think, the last thing that we were doing. Any questions on this before I erase? Denise?
Gaussian surfaces and equipotential surfaces, those aren't the same thing.
Not necessarily. When for the sphere, when we were originally pseudo-deriving Gauss's law, the Gaussian surface would have been an equipotential surface if it were a physical surface. I guess that's the big difference. It's not necessarily a physical surface. Yeah, in that case, they would have been the same, but when we did the plane and the line, they were not.
Okay.
All right, so the parallel plate capacitor hooked up to a battery. So first off, from the battery, which is the positive, which is the negative side? Or let's do it this way. So we have two leads here. One of them's positive, one of them's negative. Which one is positive?
The left one.
How do you know? All right, on the two plates right here, which one's gonna be positive plate, which one's a negative plate?
The left one be positive.
Why?
It's connected to the positive side battery.
Yep. Because electrons are basically coming out of the negative side, they're gonna start building up on this side, chasing electrons away from there. Overall, the capacitance of the capacitor is the charge divided by the potential difference between the plates. We also have that the voltage between the plates is the ED equation. Let's get slightly more sophisticated than that. The electric field is a vector. So if I'm looking at the plates here, my electric field, if that's positive or negative, my electric field goes to the right, but my change in potential is getting smaller as I go to the right. And so if we throw the vector piece into it, make it a little bit more sophisticated. We have a slightly better version of this equation. So this is if you're playing strict adherence to the math, you'll use this, or you can think through whether you're gaining or losing using that. So the first one up here properly should have absolute value signs. If in doubt, just throw them everywhere. But this is the more generalized equation. And for those who've had calculus, this is the 10-second aside. If you haven't had calculus, don't worry about that last bit. So if I'm looking at this right here, I have this distribution of charge all over the plates, a surface charge distribution. So I've got some surface charge distribution of sigma. I guess sigma and negative sigma. If that's the case, what is the electric field in between? Formula for the electric field between two parallel plates, assuming the plates are close enough to each other.
It's sigma over E. Sigma
Sigma over what?
over E, and then
Epsilon naught.
If there's nothing there, it's epsilon naught. If there's something there, over epsilon. So let's assume nothing in there right now. And sometimes to symbolize that for this, we'll just put a little zero there for this is the base capacitor without anything in there. And so that's the electric field. So this delta V here is basically ED. The electric field is sigma over epsilon naught. And the charge, well, what exactly is sigma? How would you find it? What would you need to know in order to find sigma?
Q over A.
Thank you. So the charge is sigma times the area of a plate divided by sigma over epsilon naught times the distance between the plates. The sigmas cancel out, and you're left with epsilon naught A over D. If we had a dielectric in there, then this would just be epsilon A over D instead of epsilon sub 0, which is, and then I think somewhere near the end I talked about relative permittivity. the fact that epsilon sub 0 is the smallest permittivity, and so they came up with this ratio of epsilon over epsilon sub naught is the dielectric constant. Which is equal to kappa. This is a kappa, not a K. And so in that case, therefore, this would be kappa epsilon sub naught A over D. So the lab you're doing in 2 weeks, you're basically solving for kappa. So I'm going to write over here sort of the equations that we have involved here. So C is equal to Q over delta V, and if a parallel plate is equal to epsilon sub naught A over D, or C is equal to kappa epsilon sub naught A over D. And then we have delta V is equal to negative E dot delta X, or delta V is equal to Ed. And the electric field, the magnitude of the electric field is sigma over epsilon, so not or sigma over epsilon. I've captured all of those. Questions before I actually pose a problem? So we will take our setup over here. Let's make this a 12-volt battery. We'll make these 10 by 10 meters by 10 meter plates, and the separation distance is 0.1 meters. Notice I made the separation distance to be 1% of one length of a plate, so that is considered to be close enough to be considered infinitely large plates. And so first off, what is the capacitance? What is the charge on the plates? What is the potential across the plates going from negative to positive? What is the electric field strength from the plates themselves? And what is the electric field total? These are 5 basic quantities that, well, let me just spoil some of it. On the test, there will be a question where I give you a situation like this and you have to find this, and then we'll start manipulating the plates, and you have to be able to figure out how it adjusts. Or, what I've done more recently is I give a basic situation, and then I said, these are the things you can change. What can you change in order to double the capacitance but keep the charge the same, that kind of thing. Which I find more enjoyable. Students don't necessarily, but I do. All right, so first off, what do we know? What can we figure out?
What is that last? Electric field?
This is plates, and that's total.
Oh, total? Okay. Okay.
Or why don't I guide you, since this is the first one you've done like this? What is the voltage between the plates? Pardon? Yes. Because we gain 12 volts going across, because if I do any loop, if I ever end up back where I started, the total potential gains and losses has to add up to 0. So if I gain 12 volts going across the battery, I have to lose 12 volts going across the capacitor. I lose 12 volts going from positive to negative, but I asked for the voltage going from negative to positive, so it'd be the opposite. So it'd be 12 volts. might be missing some information here. So we have A, we have D. No, we can find capacitance. Let's find capacitance. We have two formulas. First, I want to point out this first formula right here is always true. The second formula is true for parallel plates. So this is always, and this is the parallel plate capacitor, PPC. So let's plug and chug. What is epsilon sub naught? .85 times 10 to the negative 12. A, what's the area of the plates?
One, no.
Wait,
You almost there, and then you stopped short, or I missed it.
square.
Thank you. Over D,
0.1 meters.
doing the fancy math here, we end up with 8.85 nanofarads.
How do you get 8.85?
Epsilon sub naught. It's a constant. Or Carly told me. You can also find it that the Coulomb's constant or electrostatic constant is 1/4 pi epsilon sub naught. And that's roughly 9 times 10 to the 9th. It's all for epsilon. All right. Now we can find charge. How do we find charge?
12 times 8.85.
Yep. From the basic definition right there, charge is equal to the capacitance times the voltage. So 8.85 nanofarads times 12 volts.
One 106.2.
Units?
Coulombs? Right.
Close?
Nanocoulomb?
Yes.
Say what your chest says.
Or nanofarad volts. The electric field from the plates. Now, in this particular case, we have nothing in between, so the electric field is completely from the plates. There's no other way of dealing with it. And so the electric field from the plates is the same as the total electric field in this case. If we throw a dielectric into it, it's not the case anymore. But the electric field from the plates, well, we have a formula right there.
Oh, so you just do charge divided by 100, and then divide it.
Okay, so if we expand that, sigma is Q over A, epsilon sub naught. And so we have our charge 106.2 nanocoulombs divided by A, which is 100, times 8.85 times 10 to the negative third. Probably better if I change that unit instead of this one. 12 and times 10 to the negative 9. And it should be 120. Is it indeed 120?
Yes, 120.
Did I do this in my head?
No.
What did I do?
Remember it from last.
Was that?
You remembered it from last time.
No.
You did it in your head, right?
Well, I mean, I didn't do that in my head. We have another formula with the electric field in it.
Oh,
It's just the voltage divided by the distance between them. So volts per meter or newtons per coulomb, same thing. Now recognize that this formula right here, this electric field here, or here, either one, this is the total electric field. And right now, there's not a distinction. When we throw a dielectric into it, then it becomes of more critical importance. But questions right here, just with the basics.
I understand.
All right, throw a dielectric into it. So now, through the magic of a board, we fill this with some insulated material, otherwise known as a dielectric, with a dielectric strength of, we'll make it 3. So the permittivity between the two plates is 3 times that of free space. So this is initially kappa equals 1. And so now let's do it with kappa equal to 3. What is going to change, or what is going to, actually easier, what is going to stay the same?
Change in volts.
Let's work on the wording.
Change in potential. Change in potential.
Yes, there we go.
Sorry.
Or what's the other word for change in potential?
Potential.
No. Change in potential and potential are not necessarily the same thing. Volts is a unit voltage. All right, so the voltage will stay the same because it's still hooked up to the battery. If I disconnect it from the battery, then things change on that. But if it's still hooked to the battery, my voltage stays the same. So that's still 12 volts. Because my voltage doesn't change, and nothing else changes other than I stuck a dielectric into it, what else will stay the same?
Electric field.
Which one?
Total.
Yes, that stays the same. Everything else changes. All right, so I know what the voltage is. I don't know